everyone. What we're going to deal with now is very like a physics class, I suspect. So I'll apologise beforehand. This is not my forte, but I'll try my best to do it as close to the way it should be done in a physics class, but introducing, in some questions at least, calculus to aid in the calculation of what's called the hydrostatic pressure. So, come back to this in a minute. Let's just give you an overview of what's going to happen here. I want you to imagine that we're on the surface of the water. And on this surface, we have say a rectangular plate at a fixed depth. So let's say the depth is, I don't know, 10 meters. And this plate is 8 meters by 2 meters. Then we're interested in calculating hydrostatic pressure, right? How much pressure is on this plate? If you think about it, the pressure that's on it is really a big column of water. The entire water, if you imagine this going all the way up to the surface. That's what you would be calculating. Right? And so we're looking at hydrostatic pressure, the total mass of water. And you can imagine that the further down you go, like if you went down another 10 meters, that force would double because there's twice as much water above you. And there's a whole load of unit issues that we have to take care of. And then we have to also take care of the fact that you could do questions in the metric, which is when everything like here is in meters and the units would be kilograms typically for the mass of the water. And over here, you're going to get questions where everything is in feet and pounds. And when you do feet and pounds, the formula changes, the constants change. In fact, when you do foot and pounds, you don't even need gravity, which is 9.8. That'll interfere with the question. You're going to have to deal with that only when it's metric. So we are going to find the total hydrostatic pressure and the total force that would be exerted on that plate if it was horizontal. Now, I want you to imagine that the plate isn't horizontal, but it's vertical. Now, that distance there, let's say that's 10 meters. So imagine I took this plate and instead of it being flat, I made it vertical, right? So this would still be 2 meters, right? And this would still be 8 meters. But when you're talking about the hydrostatic pressure here, the pressure is different on the piece really at this top half here. At this top half here, the water pressure, although it's going sideways, is the equivalent to the amount of water pushing down on it, which is just the property that water does. So at the top here, you've got like 10 meters of water pushing on it. But at the bottom here, you're going to have, because it's 2 meters deeper, you're going to have 12 meters worth of water pushing against it. And of course, we have to incorporate the fact that the pressure at any given strip along this vertical plate changes from the top to the bottom, and it gets progressively bigger. And so in those questions, we have to figure out, that's when calculus comes in, how to adapt to this new situation. So that's kind of the overview without too many details. Let's return back to that picture or pages that I had a few moments ago. That's these guys. So the questions are 11 to 15. They are very long for the most part, and for some quite messy because of all the different balls that you have to keep juggling in the air. So let's start with a very simple shape, and this is going to be question 11. And what we have in question 11, we'll hide this. and I'll just read out what it says. It says that you have a tank. It says that, so you have a tank that's 10 meters long and 4 meters wide and 5 meters high. And it's filled with kerosene, and kerosene has a density of 820 kilograms for every cubic meter. So if you could imagine a meter by a meter by a meter cube of kerosene, it would weigh, oh, that's about over 1,600, probably closer to 1,700 pounds. It's pretty heavy stuff. We're also told that the gravitational constant is 9.8, for those who like units. It's meters per second squared. And the first question they ask us, question A, is to find the hydrostatic pressure. And the formula for getting that is rho gravity D. And they want to find the hydrostatic pressure at the bottom of this tank. So I'm going to imagine that I'm drawing the tank. Don't worry if the shapes are a little bit out, you know, dimensions. It's something to visualize. The bottom of the tank is this guy here, right? And that is made up of, because that vertical distance is what, 5 meters high, is 5 meters. And the rectangle itself is 10 meters long by 4 meters wide. So if we're talking about what the numbers are going to be for these three guys, the hydrostatic pressure is the density, rho, which is 820, multiplied by the gravitational constant, 9.8, times the depth. And if you think of this being full of water, that's essentially you've got a column 5 meters deep. And so those are the three guys that you would multiply together. And if you do this, the hydrostatic pressure ends up being, I hope, check I got the right numbers, 4, yeah. It should be 36,162. And for those who like units, I think they're called pascals. It's a unit of pressure. And that's question A done. Question B is asking us to calculate the hydrostatic force. And the formula for getting, I put little blocks around the formulas. That's the formula for hydrostatic pressure. Hydrostatic force is found by multiplying the pressure and the area of the plate together. So in this case, the pressure we already know is 36,162 times the area of this plate is what, 10 times 40. So that would be times 40. And that calculation is about 1 million. Look at it. The answer I've got here, 446, 480. And the units in this case, I believe, are newtons. So on that plate, there's over 1.4 million newtons of force. That's a lot of force. Then they go and they do question C on us. And for question C, they ask us to find the pressure on one of the plates. I believe they want us to be this plate here. So can you imagine, this is a side on. This is our plate, and it's what, 4 meters by 5 meters. And I'll do a little, although it doesn't exist, it helps me. We are basically trying to find the total amount of force on that guy who's now vertical. So you can imagine at the top, there's very little force because there's only a little bit of kerosene, but when time you do a strip down here, you're going to get a lot more. So the way that we create this, right, is we calculate a guy called the force function. And the force function is rho g, the width of a strip, times the depth. So it's a little bit cryptic, but that helps me. So what you do here is that you randomly choose a point somewhere below the surface. This is the guy I mean when I say the width of the strip. I'm just going to call it width. And this distance here, which is how far away from the top is that guy, I'm going to call that guy x. So it's going to be rho times g. Now, every single strip is the same number. So that actually is just a fixed number. It's 4. And the depth is x. So our force function is rho g times 4 times x. And so to get the total force, the hydrostatic force, you integrate from a to b the force function dx. So you're going to integrate rho g 4x dx. Now, rho and g are actually numbers, right? Rho is the density of the kerosene, which is 820, and gravity is 9.8, but it's just convenient to write them like this because the thing just gets really big with lots of ugly numbers. Now, A and B represent the values that X will take. In other words, the depth at which this rectangular plate goes. Now, right at the top, it's on the surface, so its depth is 0. And here, it's 5. Now, if you imagine a different story where the rectangle is below the surface, then A might be, oh, I don't know, 3 to 8. You know, you would adjust the depth accordingly. So this is going to be rho g, the integral from 0 to 5, 4 times x dx, which is rho times g, 2x squared, evaluated at x equals 0 to x equals 5, which in turn becomes rho g. 2 times 5 is 2550. Okay, time to start putting numbers in. The density is 820. Gravity is 9.8. And the integral part is 50. So you stick all that together and you will get 325,458. And the units here do be newtons. So the total force acting on one of the side panels would be this number here. And I said that was a long question, and it truly is. And that's only, really what I've just done is only good for questions 11 and 12. The difference in question 12 is that the units are feet and pounds. So that means this G guy doesn't matter. You only have rho and D. So rho will be the density of water, which is 62.5, and D will be in feet, 5 feet or 10 feet, whatever it might be. Our next question involves a vertical plate. So that's pretty much what all of them are going to be. This particular one is going to be a triangle where that distance from here to here is 10 meters. And that distance from here to here is going to be 6 meters. And we're only being asked to calculate the total force acting on that plate. So the guy that we're going to be dealing with, oops, is this fella here. So the force function is going to be rho, gravity, width, and depth. Well, what can we do here? It is a bit messy. I'm going to choose a random step and we'll assume that it's pretty much rectangular. If you make it small enough, it is. And we'll make that guy X. So we already have one of the two numbers. The depth of the strip is X. Now the hard part. We need to find out what the width, the distance from here to here is. And that distance will actually contain X because that width changes as you start at the top and go at the bottom. So what I'm going to have to do is do something at the side here and redraw my triangle. Put in 6 here. Put in the vertical distance 10. Put in my little strip again. Let's call the width W because it's easier to write. And let's put that distance from there to there, X. And I am going to find what W is equal to, the width, in terms of X. And the way I'm going to do it is by similar triangles. I have a little baby triangle where that distance is W and that vertical distance is X. And I have a really big triangle who is similar in shape, but whose dimensions are 6 and 10. And according to the properties of similar triangles, corresponding sides are in equal ratio. Essentially, X divided by 10 will be the same as W divided by 6. And now I'm going to solve for W. Cross multiply. Divide both sides by 10. And that is W, 3/5 X. Told you it was being X. So now we are ready to plug it in to our force function. So it's going to be rho times gravity times the width times X. And so I can now get the total force, which is all they want, the integral from A to B of the force function dx. It's going to start at 0 and finish at 10, so that's easy done. This rho and g I'll pull out, and if you multiply these together, you get 3/5 x squared dx. Add 1 to the power, divide by the new power, evaluated at 0 and at 10. Right, that's going to be 1,000 divided by 5, that's 200. So you're basically going to have 200 rho times g, okay, times to put the numbers in. Water has a density of 1,000 and gravity constant is 9.8. So that calculation, when we put it all together, should be, what have we got? Should be 1,960,000. And the units will be newtons. And that's us done. The total force acting on that triangular plate is almost 2 million newtons. when you put things under the water, and it doesn't need to be particularly deep in the water, the pressure on them, the total force acting on those objects is ridiculously large. Now 14, I'm only going to set this one up. So we have some water, and we have a triangular plate, which happens to be isosceles, but the units are in feet. Okay. Oh, and this distance here it's not to scale, it's 7 feet. So we have to figure out here the force function. The force function changes when you're using feet. It's no longer rho times gravity. It's just the density, rho, followed by the width of a strip and the depth of the strip. So I'm going to imagine a little strip here. And that, we have to calculate what that width would be for any given value, right? Essentially X. So we have a choice here. I can tell you that that distance there is going to be X, right? So I've got rho, which I'm actually going to put in as a number. It's 62.5 times the width, followed by the depth, which is X. So if we can find out what that width is, we're well on our way to solving this problem. I'm pretty sure that X looks kind of weird. Let's make it more like an X. We're pretty sure that that's going to contain X's because the width changes as you go down the shape. So let's draw our triangle. Put my little guy in here. And I know that this is 6, and this is 5, and this is 5. And if I was going to do similar triangles, this would get really ugly really quickly. And the reason for that is that this is an isosceles triangle, and the math in isosceles triangles is just notoriously ugly. So I'm going to do an adaptation. Here is the shape, and I am going to split it down the middle, which makes that guy 3 and that guy 5. And I'm only going to focus on this side. Now, if I draw this picture here, right, would you agree that the entire width is just twice whatever that guy is, right? So why don't we just call it half a width? Because that's what it is. Now, I know, I've lost my picture here because I've got so many of them. Where is it? There we go. Right, I have all the information I want here, but I want to put in this guy here and tell you that this distance here is still X. So let's see if I can construct out of this the picture that I really need to deal with. This is going to be 3. This is going to be 5. This distance along here is going to be 1/2 W. Now, if you use Pythagoras on this right angle triangle, because it is a right angle triangle, can you trust me that this distance is 4, because I need that. And I'm not going to use 5 anymore, because these two numbers are much easier to deal with than diagonal lines are. So all I need to do now is imagine my big triangle, which is 3 by 4. And then I've got a little baby one, which is this bottom half. And this guy is a half W. And this guy here, we don't really know what he is right now. So let's just call him Y. Now, what do I know about this distance is X, right? And this distance all the way from here to here, right? Well, if you notice that that guy's 7, and that this distance here is, I know it's not to scale, is 4, then won't this distance be 11? Which tells me that this guy here is 11 take away X. And so I now know that you're 11 take away X. So 11 take away X. So 3 divided by a half W will equal 4 divided by 11 take away X. And our job now is to figure out what W is equal to. If I cross multiply, 2W equals 3 lots of 11 take away X. 2W is 33 take away 3X. W then is 33 halves take away 3 halves X. We have our W. So I can now match this fella in here. So it's going to be 62.5 times that guy times him. And our force then will be equal to the integral from A to B of f of x dx. And what is the depth? Well, the first number is actually this piece here, and that's 6 feet under the water. And the last number is this piece here, which we already found out was 11. And the force function is 62.5 times 33 over 2x, take away 3, put that guy in, 3 over 2x squared dx. And that's when I'm going to stop. I would pull out 62.5 and integrate that using the power rule, and then reconstitute the question after that by multiplying. And it looks like, according to what I have here, that the answer to the total force is about 6,250 pounds. I guess I didn't promise these guys were going to be pretty, and I think it certainly lived up to that expectation. So we have one last question to deal with, and they always keep the best till last, don't they? And I would certainly say that this one is a head scratcher. What you have is a circular plate, radius 7 meters, underneath the surface, where that distance there is 3 meters. And they go and they tell us a few things that we need to know. For instance, gravity is going to be 9.8, and that density is going to be 1,000 kilograms per cubic meter. The big problem we're going to have with this question is that the normal way of tackling it is to put a random strip at a certain distance, x. But if you do that, the math just gets ugly and you can't actually solve it. So what I'm going to do instead is I'm going to use this distance from here to, well, I don't want that 7 in the base, so let me draw it again. So here's my picture without the 7 cluttering up. I'm going to put my random strip there. It might look like it's in the middle, but it doesn't need to be there. And I am not going to call this distance from here to here x. In fact, I'm not even going to call it x, because I like x for the other cases. I'm going to call that distance y. So we are going to get the integral in terms of this variable y. I mean, if you want to call it x, you can. And another reason for calling it y is because that's what WebAssign is calling it, and you have to fill in the integral. So let's take this shape and figure out how to deal with it. Well, I'm going to draw a vertical line right down the middle, and I'm going to imagine that this is where my strip is. And so the guy that I'm going to get is only this piece here. So can you imagine? I'm only going to find that guy. So he is a half W. Now I know this distance here because I've chosen it to be y. So far, so good. So what we need to do now is find some connection, right, between this side and this side, and be able to come up with what W should be equal to in terms of the variable y in this case. What else do I know that might be of use? Well, if I put the center here, then the distance from there to there is the radius, and the radius is 7 meters. So that makes that little piece here 7 take away y. So what I've now got is a half W, that bit, a little guy here, 7 take away y. That takes me to here. And now, if I draw this diagonal in, I get a radius, which is 7. So what I've done is I've created a right angled triangle that contains the side half W and the other two guys. And so I can now set up a relationship, which is Pythagoras, which says 7 take away y squared is a half W squared plus 7 squared. And that guy is 7 take away y squared is 1/4 W squared, add 49. And so 7 take away y squared minus 49 is 1/4 W squared. Multiply both sides by 4. And you get W squared. And then take the square root of both sides. And we now have W. So I now know what W is equal to. And I'm going to make a change. And it's not my fault. And I'm doing it that way because in their story, they measured y from the bottom, not the top. And so they basically switched places. what I had would be perfectly fine and it would work. Because if you have something inside the square root, it should come out both ways without too much trouble. So that's going to be the guy that we've got. So the hydrostatic force then is integral from A to B, rho times gravity times width times depth dy. I'll just keep this as A and B right now. And I'm going to pull out the rho and the g. The width is 2 times 49 take away 7 take away y squared, which is okay, it's not great. And then we have to figure out what the depth is. And that's not y. Okay, the depth is not y. They're measuring it, by the way, this guy here is 7 meters. So they're measuring y going up the way, which is to me a ridiculous way to do it, but they're going to do it that way anyway. So when we talk about what the depth is, the depth is simply just going to be 10 take away your y value. Now this integral is not feasible, not as a normal integration. So it's just going to be 6 wrong units, 1000 times 9.8, the integral, and the integral will then go from -77, because I actually said that the distance was measured from the bottom, but it's actually measured from here, so half of it goes down 7 and half of it goes up 7, which is even weirder, but that's the one that they've got. And then you do the integral of this guy, which I'm just going to go dy, and do it on a calculator, right? And you will get 15,085,928 newtons.